Welcome back to our tech podcast, where we delve into the fascinating world of database management and the challenges developers face in keeping data intact. Today, we're going to explore transactions, concurrency, and the various isolation levels in databases. Whether you're an experienced developer or just starting your journey, grasping these concepts is essential for creating reliable applications. So, let's jump right in. To kick things off, let's discuss transactions. At their core, transactions are sequences of operations that are executed as a single logical unit of work. They need to adhere to four essential properties known as ACID: atomicity, consistency, isolation, and durability. While this framework is quite powerful, it does come with its own set of challenges. One major issue arises when a transaction seems to fail due to network problems, even though it may have actually succeeded. This can lead to a situation where a client mistakenly retries the transaction, resulting in duplicate operations. To tackle this, developers often implement deduplication mechanisms at the application level, but that's just scratching the surface. Now, let's consider what happens during system overload. If a transaction fails because of high load, retrying it could make things worse. To prevent this vicious cycle, it's important to limit retries and employ techniques like exponential backoff. Additionally, distinguishing between transient errors such as temporary network interruptions and permanent errors like constraint violations can help determine when it's worth attempting a retry. We also need to think about side effects. If a transaction involves actions outside the database, like sending an email, retrying it could lead to unintended outcomes. For instance, you wouldn't want to send the same email multiple times if the transaction fails. When multiple systems need to either commit or abort together, using a two-phase commit protocol can help ensure that everything stays in sync. Now let's shift our focus to concurrency, which introduces its own complexities. When two transactions don't interact with the same data, they can run in parallel without any issues. However, problems arise when one transaction reads data modified by another, or when two transactions try to modify the same data at the same time. This is where race conditions can emerge, and they can be particularly tricky to debug, especially in larger applications with many users. To assist developers in managing these concurrency challenges, databases offer transaction isolation levels. These levels give developers control over how transactions interact with one another. The highest level, known as serializable isolation, ensures that transactions behave as if they were executed one after the other. However, this level can come with a performance cost, leading many databases to adopt weaker isolation levels. One common isolation level is read committed. This level prevents dirty reads, meaning a transaction can only read data that has already been committed. It also stops dirty writes, ensuring that a transaction can only overwrite committed data. While this sounds beneficial, it can still lead to issues like read skew, where a user sees inconsistent data if they access the database during an ongoing transaction. For instance, imagine a scenario involving bank accounts. If a transaction is transferring money between two accounts, a user might see one account's balance before the transfer is completed and the other account's balance afterward. This could mislead the user into thinking their total balance has decreased, even though the transaction is valid and will ultimately reflect the correct totals. Another challenge with the read committed isolation level is the risk of lost updates. If two transactions attempt to update the same data simultaneously, one might overwrite the changes made by the other, leading to inconsistencies. While read committed prevents dirty writes, it doesn't fully shield against these race conditions. To address these challenges, databases use locking mechanisms. When a transaction wants to modify a specific object, it must acquire a lock on that object, which prevents other transactions from making changes until the first transaction is complete. However, this can create performance bottlenecks, especially if a long-running transaction holds locks that block others, resulting in slow response times. Let's also consider the implications of using weaker isolation levels. While they can enhance performance, they can also introduce subtle bugs that are difficult to track down. For example, if a backup process runs while transactions are still being processed, it might capture inconsistent data, leading to permanent discrepancies if a restore is ever needed. In summary, transaction management and concurrency control are fundamental aspects of database systems, but they come with their own unique challenges. Understanding the intricacies of isolation levels, the importance of deduplication, and the implications of concurrency can empower developers to build more reliable applications. As we wrap up today's episode, keep in mind that navigating the complexities of transactions and concurrency is vital for creating robust applications. By being aware of potential pitfalls and following best practices, you can ensure data integrity and enhance user experience. Thank you for tuning in, and we hope you found this discussion insightful. Until next time, keep coding and stay curious.